Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We continue with our introduction module. In this fifth lecture, we continue with statistical framework, the discussion on statistical framework. In last two lectures also we discussed statistical framework. Today we will actually do some examples to explain statistical framework in details. Let's recall this. That a population is a set of all measurements of interest for some sample collected, and the sample, actually the collected sample, is the subset of the population. So, basically what we explained in terms of that coin tossing example, population is the all possible tosses, the result of all possible tosses in past, the current, present, future, all possible tosses of a coin. Population is the result of all possible coin, and sample is just a bunch of tosses that you have observed, a finite number of tosses you have observed. So, you want to conclude about the population in terms of sample. So, we want to infer about population using sample, and this takes us to the domain of probability, because the set of all possible measurement, the choice of a particular set of measurement, because just in the coin tossing example, you toss a coin, it can be head or can be tail. There is no way to for sure say that given a particular toss it will be head or tail. Realistically, what we can do, we can try to predict the chance of getting a particular one, head or tail, fairly accurately. That is all we can hope to achieve. So, this takes us to the domain of probability, and there is nothing very specific to this population and sample, this particular population and sample, like coin tossing example. In any population, when you are kind of choosing a sample, it basically can be anything in the population. So, whenever we are drawing a sample out of the population, a particular sample point has the potential of being any of the population points. So, we can talk about what is the chance of this sample being some of the population. So, just another modification of this coin tossing example, just pick randomly an Indian of age, let us say between 30 to 40. What is the chance with the person you have picked up is diabetic or non-diabetic? Well, roughly speaking, if you have chosen it randomly enough, in a fairly representative way of Indian population, the chance of the person being diabetic will be approximately same as the proportion of diabetic people in India. So, this is, but so you really cannot say that you have picked, if you are randomly picking a person, the person you will get is diabetic or not. You can at best say the chance. So, this takes us to the domain of probability. So, this inferring about population based on sample is inherently a probabilistic game. So, remember our in the second lecture we talked about this height weight example. So, we were trying to predict relations between height and weight. So, we had this, we have collected 100 data points, H100, W100, and in a very simplistic term we have kind of plotted these, and if it came like this, we said that this is kind of a representative line. This, if you kind of say that if this line is say W equal to A plus BH, this W based on this H is a sort of a good predictor, decent predictor for weight in terms of height. But here also, frankly speaking, this fitting of these line, these A's and B's, you can see that this line heavily depends on the particular sample points you have chosen. The particular data you have, this A and B depends on that particular data. So, the values of A and B, so now, but these data points also, because each of these data point, each of these sample point potentially can be any of the population points based on the distribution, I am using now the term of the population, which we talked little bit about distribution in last class. These values of A and B also are probabilistic in a sense. At best we can say that A belongs to this with this probability. So, if these sample points belongs to certain area in the, if H1, H2, H100, Hi belongs to a certain range, we can at best say that the probability of H1 belonging to this range is this, probability of H2 belonging to this range is this, etc. We can at best say that you calculate these values, you just kind of fit this line and calculate these values. We will actually get into this. At best you can say that probability of this belonging to this region is this, and not only that, you will see that what one can do, one can try to predict. Now, if you choose a 101th point, based on the distribution of the population, one can try to predict the relation between H101 and A plus B, or rather sorry, one can predict the relation between W101 and A plus B H101. You have fit the line and you are saying that this fits rather nicely in the based on this sample, you are claiming that this is a good predictor for the population, good predictor for a weight in terms of height. You can test that, and because W101 is kind of selected from the same population which has certain probability distribution, you can actually say what is the relation between these two, the predicted one versus the actual one, and let us say what is the probability that this is fairly accurate prediction of this. So, this is this kind of inference what we will keep doing. So, particularly now we are talking about ambit of all measurements versus a particular measurement. The probability of picking a particular set of measurement A out of the population X of all measurement is a number, it is a chance, it is a probability, it is a number between 0 to 1. Now, of course, probability of nothing, that you are picking something that belongs to empty set, probability of nothing is 0, and probability of everything, you pick up a population, pick up a sample and you just say it is one of the all possible measurements, that is 1. I mean, if you pick up something, it will be one of the all possible measurements. So, the chance of that being one of the all possible measurement is 100%, and if you pick up something and you say that you are picking up from all possible measurements and you pick up something and you ask what is the chance that it is none of the measurements, well, you are choosing from these. So, if you are picking up something, the chance of it being none of them is 0. So, that is one of those foundational that these facts, this probability you are taking between 0 to 1, probability of nothing is 0, probability of everything is 1, is basically part of this foundational framework of probability. It is essentially percentage normalized between 0 to 1. One can say probability, chance of getting something is 50% is same as saying probability half. So, this function P, as we saw, is something intrinsic to X and A, the all possible measurement versus the set A where you are taking certain measurements, and we discussed that like it essentially is the number, you keep picking samples and look the portion of the samples that belong to A. Now, if you take large number of samples, this portion approximately becomes something stable, and that number is this probability of the set A. So, this is intrinsic to X and A, and important goal is to basically understand, important goal of statistics is to understand this P using sample. Some basic properties of probability, if A1, A2, AK are disjoint, then the probability of everything is just the sum of the probabilities. This is basically just this intuitively, if you are having these three things: chance of belonging to this, chance of belonging to this, and chance of belonging to this together. So, the union is here, 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 well, just the sum. Now, if they are not disjoint, then it gets slightly complicated. If you ask for, this is your A and this is your B, if you are asking for probability A union B for this case, this actually you have to count A, you have to count B, but then you are over counting this region, the intersection. So, you have to subtract that, B minus probability A intersection B. So, these kind of complex formulas will come. I will give you a reference, I mean it is not possible to do a complete exposition to probability. I will give you a reference for probability book. I mean all these basic properties of probability you can review from there. Another important part is the complement set. So, if your total x, where the whole population, if this is your x, this is your A, outside of A is called A complement, this is called A complement. Now, probability of belonging to x is 1, suppose probability of belonging to A is something, then probability of belonging to A complement is 1 minus probability A. It is like chance of getting head is 70%, chance of getting tail is 30%, just the whatever is left out. So, this is these are some important properties of probability. If we need some important properties of probability later also, we will kind of recall what we need from elementary probability books and try to give you intuitive understanding at least why that works. So, just to give you an example, I will start with this coin tossing again and again. If you study any probability statistics book, you will at the first part you will almost get bored with coin tossing, but it is kind of illuminating, that is why we use it. So, this is one example. So, given a coin, we want to understand chance of getting head. Remember, we can only understand chance. It is not possible to predict for a particular toss with 100% surety whether it will be head or tail. So, now if you want to understand the head probability, suppose the chance is P for some P belonging to 0 to 1, which is a priori unknowable. Tossing coin large number of time, remember we kind of discussed that it will yield approximately 100% heads. Now, we want to guess this P. So, population is all possible tosses. Now, you do sample connection, toss the coin n times, let us denote the xi to be 1 if the ith toss is head, at 0 if ith toss is tail. This is random variable, this x is a random variable, and note that each xi you are choosing from same population. So, each xi chosen from same population so has same probability structure. As the population. Each xi has the same probability structure as the population. I mean, your xi, probability xi equal to 1 is nothing but the head probability of the coin, which is just P. It is just that you do not know how to know P. There is no obvious way of knowing P. However, if you think intuitively, as for large n, a portion of P we know that will kind of a portion of head will kind of stabilizes. A decent guess for P will be just the proportion of heads you get in the number of coins you have tossed. So, you have tossed n coins, and you denote xi to be 1 if the ith toss is head, 0 otherwise. So, if you take sum of the xi's, that gives you number of heads. So, if you divide that by n, that gives you a proportion, that gives you the proportion. So, decent guess, now how decent etc. will get into that eventually. So, a decent guess will be this proportion. Now, as we discussed earlier, for large sample this will be approximately same as actual p. So, this is what this natural phenomenon gives the reasoning, the rationale behind whatever we are doing. The question, however, the more rigorous question, for a fixed n, how good an approximation p hat is, and we will see this is actually answerable. We can understand this very well. For a fixed n, we can actually discuss how good an approximation p hat is, and not only that, there are several ways of approaching this problem. So, second example, we know, for example, we are just picking up a problem. If you take heights of all Indian people, they follow some sort of bell curve. A bell curve is so called bell curve or Gaussian curve. It's like, looks like this hat. It kind of peaks around its center, it's symmetric. So, symmetric, and as it goes to infinity and minus infinity, it just sort of flattens out. Now, the point is we want to produce the average height. So, bell curve peaks around the average height, the average. We want to guess the average height based on the heights of n people. You observe heights of n people, we know theoretically that it follows bell curve. We want to predict this center based on heights of n people. So, population, all possible heights, sample h1, h2, hn. We also want to predict how spread out heights are. So, for example, if you take the orange one, this is the highest spread. So, if you look at the orange, it has spread out highest, the maximum, then red, then green, and then blue. So, we want to predict how spread out heights are. So, this is sort of these, these are the correct values. I mean, we picked it up from internet, and you can also check it in any statistical softwares. For the blue one, basically the center is at 0. So, for blue, red, orange, the centers are at 0. The spread for the blue is actually the so called population variance is 0.2. For red, population variance is 1. For orange, the population variance is 5, and for the green, the spread is 0.5, but the center is actually not at 0, center is at -2. This is at -2, and all these are at 0. So, the goal in this problem is to, based on heights of n people, you want to predict what is the height of what is the average height of Indian people, what is the center. I mean, bell curve need not be centered around 0. Of course, for height it will not be centered around 0, it will be centered around something positive, and also how spread out it is. We want to predict these things. This is another problem like this predicting the head probability problem. So, we are getting into this setup of inferring about a population based on sample, and but remember, this is also probabilistic, because based on your prediction depends on the n people you have chosen. So, that whatever the formula based on you will predict the center or the spread will be a function of these h1, h2, hn. So, in particular, as h1, h2, hn belongs to some set with certain probability, the accuracy of this or the difference between this predicted height with, so if you take the difference between predicted height and actual predicted center and actual center will depend on h1, h2, hn. So, if h1, h2, hn belonging to a particular set has certain probability, so difference between predicted height, predicted center average height based on h1, h2, hn and the actual height will depend on h1, h2, hn, and hence it will be probabilistic. So, let us say actual let us say actual center mu, predicted center mu hat equal to some function h, h stands for height, or well, h is a bad choice because we have capital H, some function f of h1, h2, hn. So, probability of mu hat minus mu in absolute value less than equal to some c is basically equal to probability h1, h2, hn belonging to some a, where a is some, a is some set in Rn. Now, remember why this happens, because this is a function. So, this prediction you are doing is a function, you are doing a prediction based on this sample you have collected. So, this one, when you are trying to guess how good the prediction is, you want to know what is the chance of the predicted height is actually less than equal to some fixed number c. But here is the thing, this mu hat is a function of h1, h2, hn. So, mu hat being inside a set boils down to these h1, h2, hn being inside some set computed by some sort of inverse of function, and because you have h1, h2, hn, this belonging to this tuple h1, h2, hn belonging to A will basically force A to be some set in Rn. And whether you can compute this set easily or what is the characteristic of this particular set is a different thing, and those we will discuss. But precisely these are the things we have to actually discuss when we are trying to do this kind of inference. So, that is going to be one of the central topic of this kind of statistical inference. So, secondly, generally speaking, when we are talking about center, I mean tacitly in most problems we will talk about mean or the expected value of the population. So, if x random variable representing the population, this mean will just mean expected value of x, and this will just be variance of x, and this mean, these are means of the population, and this is variance of the population, and these are sample mean and variances. These are mean and variance. So, these expected values, probably for some of you it is a new thing, but these sample versions you probably have seen in school. You have bunch of numbers, you are taking average of them or kind of variance of them, this probably you have seen the school. So, the point is sample mean is, in this height example, the sample mean will be summation of the h's divided by n, is a good guess for the population mean. So, this is one of the things we will see. It is a good guess for the population mean, and sample variance is also somewhat good guess for the population variance. A fun fact, and this is something we will see in the next talk, instead of n, if you take n minus 1 below, that is also a good guess. In some places this is also called sample variance in some contexts. So, we will just use the notation we are using, but all these things, using the sample and calculating the traditional average and variance, one tries to predict the population version of that. So, that is what one thing people will do in statistics. Another thing, I mean, we were discussing this height weight thing. Another problem that is also important, that for some fixed population, as we saw, let us say people want to predict the body weight in terms of height. So, here population is, as we discussed already, all height weight pairs of all people, and then you kind of choose a sample of n people, x1, x2, xn. So, now we are denoting for this is by y is our weight and x is our height. We want to find a line that fits this data best, and the one decent guess is the least square line. So, the least square line is basically the line that predicts. So, sorry, there is a typo, this should be, sorry, this is not AI, this is a typo, not AI, this is A. So, we are trying to predict A and B, which minimizes this square distance of error. So, if you predict, so if you find A and B such that you claim y equal to a plus bx is a good guess, what you do is that, like, just pick A and B such that for each data point, you predict the y in terms of yi in terms of xi and take the square difference between actual yi and predicted yi. So, pictorially this is what you are doing. You are taking the line such that the value on the line, the actual value on the line, if you take the actual data points and take the perpendicular distance between the data point and the line and you take their squares, the sum of square is minimum. You are looking for the line where this sum of square is minimum. So, intuitively that gives you on an average the best prediction. So, you just kind of want to take a line, and based on that line, if y equal to a plus bx, you plug the sample values of x there, xi is there. So, that gives you some guess for yi, a plus a plus bxi will give you some prediction for yi, and you see that how far that is from yi in absolute terms, you square terms, yi, you subtract a plus bxi from yi and take the sum over all the i's, and you kind of try to get a and b for which this is minimum. So, now this is basically becomes a classical maxima minima problem in calculus. It is a two variable problem. So, this is basically the square distance. If you denote that by s, this is a function in a and b. You basically want to find a and b which minimizes it, and you know how absolute maxima minima is done. You kind of take the partial derivatives of s with respect to a and b and plug into 0. The solution comes out to be y bar minus a. So, a hat comes out to be y hat minus b hat x hat, where we discussed what y hat and x hat is. So, y hat is just 1 over n summation yi and x hat is 1 over n summation xi. So, your predictor for b comes out to be the ratio of these two things, and to get a you just plug into this formula to get a. This comes out using the usual partial derivative calculation, and the thing is, of course, taking partials and plugging it to 0 gives you only critical point. To check whether that is actually a minimum, you have to go to the second derivative and create this Hessian matrix, and one can check that once you do the second derivative, the determinant of that is actually non-negative, because it simply comes out to a 4n times sum of squares. So, this will be x hat here, my bad, this is a typo. So, now this sum of squares, because this sum of squares is greater than or equal to 0, and it is 0 when of course, when is this sum 0? When all the observations are same as x bar, which is kind of an uninteresting situation where all observations are identical. So, we kind of discard that case. Apart from that, it is for all non-trivial cases, this is always non-negative, it is actually always positive. So, this is a local minimum, this is a minimum for x using the calculus. So, this is the method of least squares that gives you a good fit. Now, of course, this is a guess why least squares gives you a good fit. One has to actually analyze. This has an intuitive understanding, like this gives you this sum of squared distance. But importantly, you can observe that this is of course dependent on the data you have collected. Just like the predicting head probability, you are taking just the portion of heads on those n tosses you have observed. Heavily depends on those particular tosses. Here also this heavily depends on the particular this is also heavily depends on the particular data you have observed. So, this is heavily dependent on these xi's and yi's you have observed. So, how good it is, like how if you collect new samples, how good it fits in the new sample is another question, and one needs to study that carefully. So, this is a calculation we have done. So, if you take this sample x and y as a sample data table, you can actually calculate all these things that is required here. These are pretty simple calculations, you can simplify it and fit the curve. This is how it's fit, and it turns out to be this line in the curve. So, you can see this calculation in leisure and check how it is done. Thank you very much. I stop my class here.